When a computer reads a record, the original data remains untouched. But when a computer changes a record, it initiates a series of internal physical movements that must complete perfectly to avoid error. Consider a standard operation, transferring 100 units from account A to account B. On screen, these two accounts sit neatly side by side. To a human user, this transfer feels like a single, seamless event. Account A drops, account B rises, and the overall balance shifts in unison. Inside the machine, this action is broken down into distinct sequential steps. The processor must first subtract 100 from account A, pause, and then add 100 to account B. That micropause between actions is a point of failure. In that fraction of a second, the server could lose power, the operating system could crash, or the storage drive could fail before the second step is recorded. Because machine writes happen in pieces, the core challenge of database engineering is ensuring the system can survive an interruption during that sequence. Imagine these balances are stored in a standard plain text file directly on a storage drive. If a simple application runs the transfer, it starts by opening the file and completing the first step. Account A's balance is written down by 100. If the power grid fails at this exact moment, the process stops instantly, freezing the system in its tracks. When the servers reboot and we read the file, we find a conflict. Account A lost 100 units, but account B gained nothing. 100 units have simply disappeared from the record. Because the file system allowed an isolated change to hit the disk, a mid-flight crash leaves the data in a state that no longer reflects the actual movement of assets. To prevent this, databases wrap related operations inside a consistency boundary, called a transaction. When we run the transfer again, the database intercepts the sequential changes. The subtraction and the addition are staged inside this lock, isolated from the rest of the system state. The transaction enforces a rule. Both of these changes will be recorded together, or neither of them will be recorded at all. By enforcing this boundary, the database ensures that no sequence of operations can be left half-finished, protecting the system from the chaos of hardware failure. Enforcing those transaction rules requires a specific physical architecture. Above the permanent disk storage, a server operates a layer of fast, volatile RAM. Database writes do not modify the disk immediately. Instead, the system copies the relevant data page into the volatile RAM layer. The database modifies the account balance directly inside this memory layer. The page turns amber, indicating it has been modified but not yet saved. This is a dirty page. It means the volatile memory currently holds a newer version of the data than the stable disk below it. If power is lost now, everything in RAM disappears. The new version of data is lost because it hasn't reached the physical disk. Modern hardware creates this gap. The computer processes changes in high-speed memory, but those changes aren't safe until they reach the slower, permanent disk. To bridge this gap, databases use an append-only record called the log. Before the database attempts to update the data pages on disk, it generates a record of its intent. This block notes the transaction ID, the subtraction from A, and the addition to B. The database forces this intent record into the log stream on the disk before the changed memory page is allowed to move. This rule is known as write-ahead logging. It ensures that the plan is completely safe before final data is touched. The core logic here is that the system must have a way to recover its intent before it can risk making the final change to the data pages. Because of this, data pages on a disk are often behind the curve. The log stream is the authoritative history of what has actually occurred. Once the full intent is recorded in the log, the database finishes the transaction. A commit marker drops into the stream. This commit marks the exact point where the database takes responsibility for the change. Before this marker exists, the system can discard the changes. Once it is written to the log, the system must ensure the change survives any subsequent crash. If a transaction fails, the database rejects the changes. A rollback marker is added to the log, and the pending changes in RAM are cleared. Rollback restores consistency, ensuring that unfinished or invalid operations never become part of the permanent record. Commit and rollback act as the gates that separate temporary proposals from the permanent state of the system. Consider a crash mid-transaction. The transfer begins, account A is modified in RAM, and the intent record is written to the log. Just before the commit marker can follow to permanently lock the change, the server hardware suddenly and catastrophically loses all power. The RAM layer vanishes instantly, taking the modified data pages with it. When the machine restarts, the data pages on the disk do not yet reflect the transfer. The system must now reconcile what it intended to do with what is currently on the disk. This moment of restart is when the database must prove its integrity by rebuilding the correct state from the available evidence. Upon reboot, the recovery engine activates. Scanning the log, it finds the transfer intent, but no commit marker. Recognizing the transaction never finished, the engine performs an undo, completely ignoring those changes. This ensures that incomplete work is never mistaken for the final state of the data. In a different case, where a commit marker was logged but power died before disk updates, the engine initiates a redo. It takes the logged values and applies them directly to the permanent disk. Crash Recovery uses the log to ensure the physical state on the disk matches the actual outcome of every committed transaction. This architecture provides a level of safety that a simple file system cannot match. A database write is a transition between two consistent states, using logs to govern change even when hardware fails. Finished transactions are preserved by the recovery engine, while incomplete changes are discarded to maintain the balance of the system. These systems are built to ensure that the physical record on a disk always reconciles with the logical intent of the transaction.